Today, on How It's Made. Car engines. Checking out what's under the hood. Flour. A product that's really put through the mill. Recliners. Furniture you can sit back and enjoy. And envelopes. They take a licking and keep on sticking. Car engines work by internal combustion, a process that happens in each of the engine cylinders. Air and a drop of gasoline enter the cylinder. The piston moves upward, compressing the mixture. The spark plug ignites the gasoline, causing an explosion that drives the piston downward, powering the engine. Engine components are housed in what's called the engine block. It arrives at this plant partially made. Here, they finish it off by machining the cylinder bores, the holes in which the pistons move up and down. The tool carves a crisscross pattern on the cylinder bore walls. Lubricating oil will cling to the grooves in this pattern, enabling the pistons to move smoothly. After machining, the engine block travels upside down to the engine assembly line. When it arrives there, a scanner records the block's traceability code, a barcode that enables the factory to track the block through every stage of production. As the engine block travels down the line, error-proofing devices ensure that each component is installed properly. Elsewhere in the factory, meanwhile, the crankshaft is slowly taking shape. The crankshaft is a bar that's rotated by the up and down motion of the pistons. As it turns, it transfers power to the transmission. The crankshaft starts out as a roughly shaped steel forging. Robotic arms pass it down the line from station to station until, 20 tooling machines later, it's fully formed. They install a steel disc with teeth called the reluctor ring. They heat it and press it onto the crankshaft. As it cools, it shrinks to a tight fit. This ring helps time the combustion cycle. As it spins, its teeth pass in front of a sensor which reads the crankshaft's position and tells the engine to fire the spark plugs at precisely the right moment. Now they balance the crankshaft. If it's off kilter, the engine will vibrate. A computer analyzes the spin and determines whether they need to drill out metal at certain points to achieve equilibrium. Back on the engine assembly line, the engine blocks are still upside down. A robot lubricates the 4 bearings on which the crankshaft will turn. Then it drops the crankshaft into position. The pistons come next, 6 per engine, because these are 6-cylinder engines. The pistons are made of aluminum. Robots install them into the cylinder bores of the engine block. A steel connecting rod attaches each piston to the crankshaft. Now workers can close up the back of the engine block. A robot applies sealant to the rear cover. They bolt it on manually with a tool called a multi-spindle torque gun. On another line, they assemble the 2 heads that'll cover the top of the engine block. This robot is applying sealant to spark plug tubes before inserting them into the heads. The heads cap off the cylinder bores. They provide each cylinder with a spark plug and 4 valves, 2 for allowing the fuel mixture in and 2 for releasing the exhaust. The black tubes running front to back are the camshafts, the components that open and close those valves. There are 4 per engine. A robot applies sealant and then bolts a cover onto the front of the engine block, the head, and a component called the timing chain. This chain connects the crankshaft to the camshafts so that they rotate in unison. This ensures the valves open when the pistons are in the right position. Finally, they spin the engine mechanically to make sure the components function properly. The grain most commonly ground into flour is wheat. Flour mills use high-protein or hard wheat species to make bread flour, and lower-protein or soft wheat species to produce cake and pastry flour. All-purpose flour is a compromise with medium protein. As soon as the wheat shipment arrives, a grain probe vacuums up samples from throughout the load. If the samples pass quality inspection, the mill gives the truck the go-ahead to dump the wheat to an underground conveyor. From there, the grain goes into a cleaning machine where a system of sieves removes impurities such as straws, sticks, and grain dust. The wheat then goes into storage silos until milling time. The protein content of wheat varies by species, so the first step is to blend together the right varieties of wheat for the type of flour they'll be making. From the blender, the wheat goes through a second, more intensive cleaning system that removes the tiniest of impurities, such as weed seeds and dust. On the way to the milling machines, a scale tracks production quantities. This mill's vertical production line is 5 stories high. Gravity carries the wheat downward through a succession of milling machines. Each one grinds the grain between steel rollers, then sifts it. Particles too large to pass through a sieve continue downward into the next milling machine, and so on. By the last machine, whatever's still not fully processed gets vacuumed up to the top to begin the cycle again. Mills make white flour by grinding only the wheat kernel's soft inner part, called the endosperm. This requires removing the bran, the kernel's hard skin, and the germ, its seed. That separation begins as soon as the wheat kernels enter the very first milling machine. Rollers break off the germ and bran and crush the endosperm into pieces called semolina. Sifting removes the germ and loose bran pieces, but much of the semolina remains covered in bran particles. So between each milling station is a purifier, a machine that uses controlled air currents to float the lighter bran above the heavier semolina, enabling sieves to separate the two components. The semolina goes through repeated grind, sift, and purify cycles until it's completely clean. Only then can it be finely ground into flour. The ground semolina passes through a series of sieves. This ensures it doesn't leave the final milling machine until it's been ground to just the right powdery texture. There are 3 main types of white wheat flour. Bread flour has high protein, enabling dough to rise well and bake to a firm texture. Cake flour has low protein, which produces a crumbly texture. All-purpose flour is the compromise. Its medium protein content makes it suitable for baking both bread and cakes. By the end of production, the flour mill has produced 3 distinct products: bran, used for animal feed and baking; white wheat flour, of course; and wheat germ for the health food market. Leftover byproducts go into livestock feed. In the mill's quality control lab, they bake the product for which the flour is designed, then examine its appearance, texture, and taste. They use specialized equipment to calculate the volume, the density, the protein, and moisture contents. With baked goods destined for retail sale, like these cookies, it's especially important to measure the dimensions. If the dough overexpands, the cookies won't fit in their package. Just prior to packaging, the mill enriches its white flour with vitamins and minerals. This replaces the vitamins and minerals lost when the milling process removed the bran and germ. They shake the bags to settle the flour. Bagged flour in various sizes goes out to supermarkets, restaurants, and commercial bakeries, while tanker trucks ship bulk flour to large industrial bakeries. The first reclining armchair was introduced by the La-Z-Boy Company in 1928. Today, many companies make motion furniture, as the industry calls it, and the term recliner no longer refers to just armchairs. You can buy reclining couches and even reclining sectionals. This factory makes reclining chairs and couches in both fabric and leather. The furniture construction is the same regardless of the material. However, leather upholstering requires a few extra steps. They begin by inspecting the hide, marking serious defects with one color of tape and minor imperfections with another. A computer-programmed cutting machine scans and registers the tape markings, then automatically cuts and discards the defective parts. It cuts upholstery pieces for hidden areas, such as the undersides of seat cushions, from the imperfect leather, and visible parts from the flawless leather. Once all the pieces are cut, they sew together the back, seat, and arms. Then they stuff the arms and back. They position the open end against a blowing machine that fills it with polyester fiber. Workers weigh each part before and after filling. This ensures they've blown in the right amount of fiber and also that both arms have equal filling. Next, they'll fill the seat with foam. A compression machine squeezes it, then a worker sprays on silicone lubricant. This enables the seat cover to slide on easily. Foam is made of a chemical mixture, the formulation of which determines the density. The higher the density, the higher the quality. Elsewhere in the factory, meanwhile, they cut the frame components from plywood using a computer-guided bandsaw. These long pieces will form the seat frame. A three-seater couch has 3 separate frames, enabling each seat to recline individually. A machine lines one side of each piece with steel spring clips. A worker then dabs the ends in glue and assembles the pieces, reinforcing them with long glue-coated staples. As the staples enter the wood, friction-generated heat melts the glue. The glue then dries, securing the staples. Now comes the step known as springing the seat. They hook 5 thick steel springs into the spring clips, then hammer the clips closed to lock the springs in place. They connect the springs with a plastic-covered wire so that when you sit on the seat, all the springs react in unison. They assemble the frame pieces for the arm using glue and glue-coated staples again, plus a few screws at strategic points. They screw the arm to the seat and begin upholstering. First, a layer of felt to cushion the springs, then wood, cardboard, and foam to form the rounded shape of the armrest. After lubricating with silicone spray, they slip on the leather and staple it into place. They upholster the backrest and sides in the same manner. The reclining mechanism arrives at the factory with the sides pre-assembled. Workers install the connecting pieces, then a bushing that reduces the noise the mechanism makes, then a spring to control the recline speed. They screw the mechanism to the seat frame, then hook up the operating handle and test it out. To cover the back of the furniture, they attach metal tacking strips to the leather, then turn the edge under and hammer the tacks into the frame using a pneumatic hammer. The last step is to attach the back to the seat. There's a detachable flap at the bottom, providing access to a locking spring inside that lets you remove the back if you have trouble getting the furniture through a doorway. At this factory, workers are encouraged to lie down on the job, but only to inspect the furniture. After examining the fabric and sewing, they assess the comfort and test the reclining motion. Talk about a cushy job. We rip it open with barely a thought, more anxious to read its contents than to take a moment to truly appreciate its form and function. And then we ruthlessly discard it. The humble envelope just doesn't get much respect, despite its distinguished 4,000-year history. As early as 2000 BC, the Babylonians baked special clay wrappers to transport documents. Eventually, people made envelopes from lighter materials, such as animal skins and leaves. By about 1000 AD, it became the custom to simply fold a letter and seal it with a drop of wax. But everything changed in 1837 with England's new penny postage system. To mail a letter, the sender now had to buy a postage-paid paper wrapper that folded into an envelope. One of the many envelope styles this factory makes is a 30 by 46 centimeter envelope made of natural color craft paper. A machine appropriately called the sheeter cuts the roll into 53 by 63 centimeter sheets. A worker selects the cutting die for this style and installs it on an automated press. As each stack of sheets passes underneath, the press applies 10 tons of pressure, forcing the die right through like a giant cookie cutter. The shaped sheets are called envelope blanks. Workers now load the blanks into the feeder of an automated piece of equipment called a blank sheet envelope folding machine. As we see here in slow motion, revolving steel blades first make score lines, 4 in all. 1 down each side, creating the envelope's side flaps, 1 across the top, creating the seal flap, and 1 across the lower end, creating the bottom flap. Folding blades hold the paper down along the score lines, while arms push up from underneath, folding the side flaps toward the center. Just before the flaps meet, the machine runs a line of glue down their edge. The flaps adhere to each other, forming the center seam that runs down the back of the envelope. The machine then glues the bottom flap and folds it closed. You can see in slow motion how it also applies glue to the seal flap at the top, keeping that flap open so that the glue will dry. The sender has to just remoisten the glue to seal the envelope. The finished envelopes exit the folding machine and enter another machine that counts them and stacks them upright. This more sophisticated piece of equipment is called a web roll envelope folding machine. They feed the roll of paper directly into the machine, and as we see here in slow motion, it does everything from cutting, scoring, folding, and gluing the blanks to counting the finished envelopes. For this style, a die even punches out an address window in the front of the envelope. This all-in-one machine goes through all the steps at lightning speed, 20 envelopes per second. The thin, transparent film that covers the address window is usually made of polypropylene. The machine cuts it to size and glues it to the envelope. This machine doesn't have folding blades to hold the paper down along the score lines. Instead, the blanks roll through a series of rotating cylinders with air holes. A suction system vacuums the blank to the cylinder while the operation is being performed, then releases the vacuum to transfer the paper to the next cylinder, where it's vacuumed on for the duration of the next operation. Internal mail envelopes are opened and closed repeatedly, so they don't have a lick-and-stick seal flap like regular envelopes do. As we see here in slow motion, an automated machine rivets a cardboard button to the back of the envelope. At the same time, it rivets another button with a piece of string to the flap. Envelope factories use many different types of paper, from top-quality vellum to craft paper. With printing equipment incorporated right into the folding machines, they can print return addresses, even elaborate custom designs. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.